Okay, welcome back all to this video, and here actually we will see the crystallographic planes and how a particular plane can be drawn. Okay, the last video we have discussed about the crystallographic directions, how to draw a particular direction, and what are the basic particular significance of these crystallographic planes as well as directions. Okay, here also we will use Miller indices. Here Miller indices, the definition is like based on reciprocal of the intersection of the plane with cell axis indicated with parenthesis HK and L. It was this technology was actually developed by the scientist named as William H. Miller. Okay, he was a professor in mineralogy in Cambridge. He was very much interested in this, studying the various unit cells and the crystal structures. And for the during his experiments, he found this atoms was it was very difficult to express the atoms in our engineering language, and for the easier representation of the directions of these atoms and the plane in which these atoms lies, he used this technique. Okay, here for all the cubic structures we use this technique. Okay, and cubic structures means symbol cube, FCC and BCC. For these three structures we will use these Miller indices. And for hexagonal close packed structures, actually we use another technique known as Miller-Bravis index, or that kind of representation we use. Okay, now let us see what this represent. Okay, actually let us see this figure. Okay, this one consists of many planes, and let us see how these planes are drawn. Okay, let us start with some simple plane 1. Okay, here okay, now let us see this plane 1. This is the plane. Okay, and this plane 1 is represented using this. Okay. This is plane 1. This is plane 1. Okay, now let us see how this plane is drawn. Okay, so we can see that in x-axis, this is the x-axis. This plane, can you identify at which point in x-axis this plane intersect? Okay, so the intersect, this plane 1 intersect x-axis at infinity. Okay, and we will represent it as the reciprocal. Okay, as we mentioned earlier, we will represent it as the reciprocal. So 1 by the infinity. Okay, this part. And now move to the next axis. We can see that this is the y-axis. Okay, and we can see here that at this point the plane 1 intersect with the y-axis, so the value will be 1. So it's intersect at, imagine it intersect at point 1. So anyway it has an intersection, so it will intersect at 1. So here we will write the reciprocal as reciprocal as 1. It's reciprocal. And again, now moving to the next axis, that is z-axis. Let's see which point it will intersect. Again, the plane 1, we can say that it will intersect z-axis at infinity. Okay, no intersection is there, or we can say that it will intersect only at infinity. So here we will write the reciprocal, that is 1 by infinity. Okay, so this on conversion. Okay, 1 by infinity means 0, 1 by 1 is 1, and 1 by infinity again is 0. So that's any plane represented by 0 1 0. Okay, any plane represented by in this fashion or with this number will be this particular plane. Okay, and in some textbooks, you can see some other planes, because as the origin changes, they will as origin changes, the plane will also change. But for the time being, just understand the concept like this. Okay, now moving to the next, that is plane 2. Okay, where lies the plane 2? So I am going to draw that plane in particular. So this is the plane 2. Okay. This is plane 2. This is plane 2. Now let us see how on where it will intersect. Now first, as usual, we will take the x-axis, and we can see that the plane 2, sorry for my drawing, this is the thing, so it will intersect at this point in x-axis, and let us take this as a unit 1. So as the reciprocal part, we will write it like 1, and again next in the y-axis we can see that it's having an intersection at another point, that is 1. Okay. And in z-axis, this plane where it intersects with the z-axis, any intersection is there? No intersection is there. So we can imagine that it will intersect at infinity. So we will write it as 1. So, and if we draw a plane here, then it will look like this. This is the plane 2. So the value will be represented as the reciprocal of their intercept. Okay, intercept are 1, 1 and infinity, and taking the reciprocal of those intercept, we can get this value 1, 1, 0. So this is the Miller index representation of the plane number 2, that is 1, 1, 0. Now moving to the next plane. Okay, moving to the next plane, that is plane number 3. Okay. Now here, as usual, we can see that this 1, 1, 1. So that plane 3, let me draw the plane 3 for the easy representation. Let me do it with highlighter. This is plane 3. Since many colors are here, so it will be hard to identify, but just adjust. Okay, so plane 3, plane 3, actually we can see that this plane just intersect on x-axis at point 1, and intersect y-axis at again at 1, and again it got an intersection here at z, so it will be 1. So we can know the intercept as 1, 1 and 1. So here we will write the reciprocal 1 by 1, 1 by 1 and 1 by 1. So the plane can be represented as 1, 1, 1. So any plane represented by 1, 1, 1 will look like this if the origin is taken as this. If the origin is taken as this, then again the value will change. Or if we take the origin as this, the direction of the plane will change, but all these directions are represented on basis of this origin. Okay. Now let us see the next one, that is the plane number 4. Okay, this is plane number 4. So where we can see the plane number 4. So the plane number 4 can be drawn like this. Okay, this is the plane number 4. How to find the Miller indices for this plane number 4? Okay, so here we can see that like it intersect at x-axis at 1, it intersect y-axis again at 1, and you can see that it intersect at z-axis exactly at the half or middle. So I will write it like 1, 1 and half. Okay, so on taking the reciprocal, we can take it like 1 by 1, 1 by 1 and 1 by half. So on the values will look like 1, 1, 2. So any plane which represent 1, 1, 2 with this origin will look like this. Okay. So next one is the plane number 5. Now let us see, this is the plane number 5. This is plane number 5. Okay, plane number 5, and let us see how we can show these values. Okay, you can see that again this is very simple. In x-axis it intersect at exactly at half. Okay, and y-axis it intersect at 1 unit, and here it is just more than half, and we can imagine that it will intersect at the 3/4 portion. So 3 by 4 this point on z-axis. So again we will write it as 1 by 1, 1 by half, and 1 by 1 and 1 by 3 by 4. Okay, so we will, there's a little twist in this representation. We can see that the value will be like here it will be like the values will be like 2 and the value 1, and it will be like 4 by 3. So in order to normalize, what we will do? Okay, in order to normalize or just remove the fractions, we will multiply it with the common denominator, that's 3. Okay, on 3 we will, if we multiply, we will get the value as 6, and here it will be 3, and here it will be 4. Okay. So this is what it is represented here. Okay. So the parallel planes, next we want to consider that the parallel planes have the same value. That means if 1, 1, 1, it will be like same. 2, 2, 2 will be same, or we can call it as a parallel plane. So if it 1, 1, 1 like here, it's a top view, and like if you are going to see, that means another 2, 2, 2, it will be like a parallel planes. So as we discussed here, no fractions are allowed. We need to convert it into the possible integer values, like similarly like this. And similarly, as we have done for the directions, here also we have that negative direction for the planes which comes in the negative coordinates. Okay, that HKL values of the parenthesis, we will write just a bar on the top. So this, if we find a bar on the top, then it symbolizes a negative value or a negative plane. Okay, I think everyone got the concept of this one. And to just wind up, we will see this, what is a Miller indices. Okay, a Miller indices means Miller indices are the whole numbers. Okay, few, sometimes you can get some definition, to write some definition. Miller indices are some whole numbers, okay, enclosed in this round brackets, and they are used to indicate the crystallographic planes, and it will be written like in this form H, K, and L. And if it is some like 4 or 5 more question, you need to explain some more details with some neat sketches and all. And imagine a cube like this, and if this is the origin and this is the value or the intercept on the x-axis as A, intercept B and C are the distance along x, y and z axis. And the steps for finding, we can write like this. First, what we will see is that first we will see the intercept, okay, intercept. And imagine this figure like this, and such a plane is taken, and what we will do is that we will first find the intercept along x-axis. Here x-axis it is 1/3, and along y-axis it intercept at point known as 2/3, and along z-axis it will intercept at unity or 1. So the intercept is taken as 1/3, 2/3 and 1, okay. And the reciprocal, we will take it as 3, 3/2 and 1, the reciprocal of the above mentioned intercept, okay. And if it is a fraction, like we see whether it is a fraction, and if it is a fraction we will change it to this way, multiply it with the common fraction. Here the common fraction is just 2, okay. The common fraction, we will get these values, and this value is represented as Miller indices. And once again I remind you that this Miller indices representation is just for the cubic unit cell. If it is some other kind of unit cell like hexagonal unit cell, it will be entirely different. And I think and I expect, for your syllabus point of view, this simple cubical unit cells are of much importance. And that's all for this video. In the next video we will see some more practices regarding these crystallographic planes. So thank you for the